This is the lecture for Module 3 of Unit 4. Here we will look at problems involving equilibrium constants and concentrations that appear in reaction quotients Q. Mathematical problems with K and concentrations can be loosely grouped into two types. Type 1 is the easiest type. In a type 1 problem, you are given equilibrium constants appearing in Q, the reaction quotient. For example, you'll be given concentration C, D, A, and B, or else you'll be able to solve for them. And then you're asked to calculate K, or you're given K and told the system is at equilibrium and given all but one of the concentrations, and then you solve for the remaining concentration. Type 1 problems, if you understand that K equals Q at equilibrium, are essentially algebra problems, and no examples will be addressed of most type 1 problems in this lecture. We can look at an example of a tricky problem. This is something, as you will see, it has elements of type 1 and type 2. Essentially, it's very close to a type 1 problem. You can ask if a system is at equilibrium. Right, consider this reaction, for example. Carbon monoxide and water combine to make formic acid. Now, this is an equilibrium system at the temperature at which we're going to consider the problem. Kp is 6 times 10 to the negative 7. And here we consider Kp because all three of these substances are gases. Okay, so in this problem we have a mixture at 400 Celsius, which we will assume that this is the temperature that corresponds to this Kp. And we have 0.04 moles of the carbon monoxide and 0.022 moles of the water, and 3.8 times 10 to the negative 3 moles of the formic acid, and a 2.5 liter container. In other words, our container contains a mixture of the three gases. Alright. The questions we will answer at this point is the system at equilibrium? And if not, will it proceed to the right or the left? Alright, to address this problem, you will first need to find Kc, and then you can use this data to calculate the concentration of all three species in the reaction and calculate Q. Then you will be able to answer the question, are we at equilibrium, or will we start from this point and make more product, or will we start from this point and make more reactant? Alright, you can attempt these calculations before continuing. Alright, let's look first at finding the Kc from the Kp. Here we have the formula. Kp is Kc times RT to the delta N, where the change in moles of gas, according to the balanced equation, 2 to the left, 1 on the right, so the change in moles in the reaction is negative 1. So Kp in this case is Kc times RT to the negative 1, or Kc over RT. So Kc is Kp times RT. Alright, we have a value for Kp. Note, we will use the liter's atmosphere value of R, and note also that we need to express the temperature, which we know is 400 C in this case, in Kelvin. Alright, the number that comes out of this calculation is 3 times 10 to the negative 5. Right, again, no, liters, atmospheres version of our temperature, well, 673 is 400 Celsius expressed in Kelvin. Right. Now, compute the reaction quotient Q, formic acid concentration over CO concentration over water concentration, and compare to our value of Kc to see if we are at equilibrium. If you calculate the concentrations, you should find that the formic acid concentration is 0.0015, and that the values of the concentrations in the denominator are 0.016 and 0.0088 for CO and for H2O. Now these concentrations were obtained by dividing moles of each species given by 2.5 liters. Now to two significant figures, this gives a value of 11. Right, so Q, the reaction quotient, is much larger than Kc. Right, this system is not at equilibrium. To get to equilibrium, Q has to become smaller. The number Hc, the concentration of HCHO2 in the numerator should decrease, and the concentration of CO and of H2O should increase. This concentration will decrease and these concentrations will increase if the reaction runs to the left. The reaction will move to the left to reduce the size of Q until it equals Kc. And that is the answer to the question. Alright, this problem had several components to it. We had to convert from a Kp to a Kc, and we had to calculate a Q and compare to that Kc. This is about, again, predicting whether the reaction will run to the right or the left is the trickiest or most conceptually challenging sort of type 1 problem. Type 2 problems are more difficult than type 1 problems. In these problems, you are given an initial set of concentrations and an equilibrium constant, and you are asked to find the equilibrium concentration. You will see many of these problems in this course, and the strategy will always build the same. Build a concentration, quote-unquote, ice table based on the stoichiometry of the system. ICE is an acronym standing for Initial Change Equilibrium. The best way to study this approach is by example. Let's take H2 plus I2 goes to 2 HIs. Alright, we put 0.2 moles of H2 and 0.2 moles of I2 in a 2-liter vessel. What will the concentrations of reactant and product be at equilibrium? And we have a Kc value. Right. At equilibrium, K is equal to Hi squared, concentration, over the concentration of H2 times the concentration of I2, and this equals 49.5. An ice table shows initial concentration. Specifically, it shows the initial concentration of each species in the equilibrium law, or equilibrium expression. All right, so once we've written down the equilibrium expression, we know what species to include in our ice table. Those would be H2, I2, and Hi. Further, we know the initial concentrations of each because the problem tells us so. If we divide moles by liters, we find that the concentration of H2 and I2 are each 0.02, and there is no Hi present. Okay, if you consider the value of Q under the initial conditions, clearly, well, Q would be 0, and the reaction is going to need to run to the right. Right. The reaction must go to the right until Q equals 49.5. If the reaction runs to the right, the concentration of H2 and I2 will go down a certain amount. Because of the balanced equation, 1 mole of H2 to 1 mole of I2, the change in concentration for these two species is the same amount. We'll call it minus X. Meanwhile, the concentration of HI is increasing by 2 times that amount. Sorry, I had to correct typo at that point. Alright, we can then express the equilibrium concentration as the initial added to the change. So H2 will be 0.02 minus X. The I2 concentration at equilibrium will be 0.02 minus X. And the HI concentration will be 2X, 0 plus 2X. Alright, now let's consider a solution in which we solve for X. K is 49.5, that appears on the left. On the right, we have 2x squared in the numerator. In the denominator, we have for H2 and for I2, we have 0.0200 minus x. So you multiply both of those together, and the denominator is 0.02000 minus x squared. Right. At this point, you could take square root of both sides. 7.04 is 2x over 0.0200 minus x. Multiply both sides by the denominator. This leaves 2x on the right, and on the left makes 0.141 minus 7.04x. 9.04x then is 1.141, and we can solve for x, obtain the value of 0.0156. Alright, solving for x is key to success, but you have to remember what x means. For example, the HI concentration is 2x, so we need to multiply this number by 2 to find the HI concentration at equilibrium. The concentration of I2 and H2 were 0.0200 minus x, so we subtract this number from 0.0200, and the value I obtain is 0.0044 for these concentrations. Corrected typo. Alright, let's look at another one. 2 bromium chlorides go to bromine plus chlorine. Kc for this reaction is 0.145. If we put 0.05 moles of bromium chloride in a 1 liter container, what are the equilibrium concentrations of the 3 gases? Now you should attempt this problem using the methods of the previous example before moving on. Here is the equilibrium expression and ice table for this problem. First we write down the equilibrium expression, which has a bromine and a chlorine in the denominator and the square of the bromine chloride concentration in the denominator. I'm sorry, these 2 species are in the numerator and bromine chloride is in the denominator. The value of K is 0.145. Alright, if we put in initial concentrations, the initial concentration of bromine chloride is 0.05, and the bromine concentrations and chlorine concentrations are 0. We should deduce that the reaction will go to the left. Alright, that means the concentration of bromine chloride will go down, whereas the concentrations of bromine and chlorine will increase. If we call the concentration increase of bromine and chlorine X, the change in bromine chloride is negative 2X. This is the easiest way to define the change X for this problem. Then at equilibrium, the values of bromine and chlorine will become X, and the equilibrium value of the bromine chloride will be 0.05 minus 2X. All right. Now, as before at this point, the goal is to solve for X. Here then is the arithmetic. 0.15 equals bromine concentration times chlorine concentration over bromine chloride concentration squared. That's X times X over 0.05 minus 2X squared. Again, we can rewrite this. 0.145 equals X squared over 0.050 minus 2X squared. Again, we could take square root of both sides, producing 0.381 on the left and X over 0.05 minus 2X on the right. Right, multiplying through by the denominator, 0.050 minus 2X produces an X on the right, and 0.019 minus 0.381 times 2X on the left, or 0.019 equals 1.762X. X is then 0.011. 0.011 then is the concentration of bromine and chlorine. And the bromine chloride concentration is 0.05 minus 0.011 times 2, or 0.028. Note I had to correct a small arithmetic error there to obtain the correct answer. As you can see, these problems require careful algorithmic or stepwise approach to obtain solutions. In cases we've looked at so far, we've been able to solve for X without making any approximation. In both cases, because we could conveniently take the square root of both sides of an expression. Another approach to solving this sort of problem sometimes occurs, or often occurs, I should say, when Kc is very small. All right, consider this reaction, in which two HCl's and an I2, HCl is a gas and I2 is a solid, react to make two HIs and a chlorine, both of which are gases. Alright, Kc for this is actually extremely small, 1.6 times 10 to the negative 34. Assume an initial HCl concentration of 0.1. What are the equilibrium concentrations? When we write down an equilibrium expression, we get Kc as Hi squared times the chlorine concentration over the concentration of HCl squared. Note that the iodine concentration disappears because it is a solid and does not appear in the equilibrium expression. Right, the ice table in this case has HiCl2 and HCl in it. Initial concentrations of the product are 0. Initial concentration of the reactant is 0.1. We know the reaction has to run to the right. We don't think it's going to run to the right very far, but the concentration of HI's change to the concentration of Cl's change will be 2x to x by stoichiometry, and then the concentration change of HCl is minus 2x. This gives 2x, x, and 0.1 minus 2x as final concentrations for the three species in the equilibrium expression. Okay, again, now we know the reaction has to go to the right. But the equilibrium constant is 10 to the negative 34, so not very far. So x probably is going to be very small compared to 0.1. And solving this problem will hinge on treating 0.1 minus 2x as if it was essentially the same as 0.1. Now again, we are able to do this because Kc is very small. Alright, Kc then, 1.6 times 10 to the negative 34 is 2x squared times x times 0.1 minus 2x squared equals 4x cubed over 0.1 minus 2x squared. However, if we neglect the 2x in the denominator, this expression reduces to Kc is 1.6 times 10 to the negative 34 equals 4x cubed over 0.1 squared. If I solve this algebraically, 1.6 times 10 to the negative 34 times 0.1 squared divided by 4 is x cubed. You should verify on your calculator that this number is 4 times 10 to the negative 37, and that the cube root is 7.4 times 10 to the negative 13. Right, clearly x is very small if we adopt this approach. We're going to assume this approximation is valid. And so at equilibrium, concentration of HCl is 0.100 to 3 significant figures. Concentration of Cl is x, Cl2 is x, 7.4 times 10 to the negative 3. And the concentration of Hi is going to be twice that, or 1.5 times 10 to the negative 12. Alright, this concludes this lecture. The next module will look at a particular set, or a particular type of type 2 problems involving ions in solution.